All right, so let's welcome first speaker of the afternoon, Jae Hyeok Chang, from Johns Hopkins and University of Maryland, and he will tell us correlating gravitational wave and the gamma ray signal from primordial black hole.
Okay, thanks for the invitation.
Recording in progress.
Okay. So let me start by talking about the primordial black holes, but I'm going to focus on asteroid-mass primordial black holes, which means the primordial black holes I'm considering has very small masses. But you may why asteroid mass? And actually there are a lot of regions, and like for example, it's less constrained, and there are upcoming gamma ray observations and clear production mechanism. And our main point is there's a correlation with gravitational waves. I'm going to go through this step one by one. So let me talk about the constraint first. So this is the plot, PBH constraint plot from the one of the like PBH like snowman white papers. So these are very up-to-date plots. Here, x-axis is the primordial black hole mass, here shown as compact object mass in terms of solar mass, and y-axis is the dark matter fraction. So mass density of the primordial black hole divided by the observed dark matter mass density. And here the blue shaded regions are the PBH constraint with more conservative assumptions. And this gray region here is not very shown maybe, but there's a gray region that is the same constraint with less conservative assumption. So you can just think these blue shaded regions are actual constraints, and the all yellow regions are future sensitivities. And of course, like from obviously from the quantity, there's interesting parameters. PBH can the mass fraction of the PBH can be as large as 1, which is this region. So this region is for the small mass black hole. This region and this region is for the asteroid mass primordial black hole. You cannot go below this mass because this is below this mass has a lifetime less than the age of the universe. So those primordial black holes like already evaporated, and the upper range is like mostly given by this anterior micro lensing constraint. And there's another interesting parameter case, a little higher mass can be around like F can be order 10⁻⁻⁻⁻⁻⁻⁻⁻⁻ is called planetary mass primordial black holes, but of course in this talk I'm going to focus on asteroid mass primordial black holes. This asteroid mass primordial black holes is around from 10⁻⁸ solar mass to roughly 10⁻⁻11 solar mass, and in terms of grams, it's like 10⁻15 grams to 10⁻22 grams. So this is the region where we can achieve PBH equal to around 1. Okay. Then the second reason is there's upcoming gamma ray observations. Of course, we know from the black hole emits the Hawking radiation with a Hawking temperature, which inversely proportional to the black hole mass. So small black hole mass means larger Hawking temperature, and so black hole emits like more energetic and larger number of particles. This Hawking temperature for the asteroid mass size black hole is correspond to around MEV. So asteroid mass black hole MEV scale photons, and these photons can be detected in future gamma rays, such as e-ASTROGAM or AMEGO. And this line is for the sensitivities for e-ASTROGAM, and here is for AMEGO. And the other lines are from the constraint of the existing observations. So from these new upcoming observations, we can prove this region, which covers photon energy from around 0.1 MeV to 100 MeV. And this energy corresponds to primordial black hole mass between 10⁻14 gram and 10⁻17 gram, which is like a desired asteroid mass PBH. So from these upcoming MEV gamma ray observations, we may detect the primordial black holes in these mass ranges. And this is well studied by Coogan, Morrison, and Profumo. And as I told you, this yellow regions are feature sensitivities, and this the most left corner feature sensitivity is from this AMEGO gamma ray observation. So in this range, PBH can be detected in near future. So we focus on this mass. This mass is the most interesting parameter space from our point of view, that it can be discovered like soonish. So with this, we can also think about the production mechanism for this very small mass primordial black holes. And there's a very well-known production mechanism because first of all, these small mass black hole cannot be produced from the astrophysically. Like it's hard to produce them by like collapsing of like stars or like merger events, because they predict much higher mass black holes, and it's the planetary event. But there still can be possible to have these small mass black holes cosmologically. So in the early universe, we can think of very larger curvature perturbations or like density perturbations. Then whole Hubble patch can have the density contrast larger than the critical density. Then with these larger perturbations, then this whole Hubble patch can collapse into a single black hole. And this depends on the K mode, and if we have like large curvature perturbation at a certain K, then like once this K mode enters the horizon, then this whole Hubble patch collapses to the black hole, and we can calculate the time that this K mode enters to the horizon, and then we can calculate the total energy of this whole Hubble patch, and that gives the mass of the primordial black hole. So for KP here, KP is like K peak in this curvature perturbation corresponds to 10 to the 15 inverse megaparsec. We can have like around 10 to the 17 gram of primordial black hole, which is asteroid-mass. But of course, to have this feature, the whole Hubble patches collapse to a single black hole, we need very large amplitude of these curvature perturbations, like mainly order 1. But of course, this large perturbation is constrained very tightly, especially for large scales from BMD and large scale structures. But for small scale, like namely K is much larger than 1 inverse megaparsec. There's much less constraint, so we can achieve such large perturbation. And clearly, you can see from here the K mode that gives the asteroid-mass black hole is much larger than the CMD constraint, which is around inverse megaparsec. I'm going to be back to this point in several slides, several pages. And thinking about this production mechanism, we can make our main point. We can have correlation with gravitational waves, because these gravitational waves are necessarily produced from the curvature perturbations. So once we have that large curvature perturbation, it naturally gives these gravitational waves at second order. But of course, this gravitation is very suppressed because this is second order, but we think about very large amplitude of the curvature perturbation. So still at second order, we can still have sizable and large enough gravitational waves that can be detected in future gravitational wave detectors. So we can also calculate the frequency of gravitational waves in terms of like KP. And for the 10 to the 15 inverse megaparsec, that gives the asteroid-mass size PBH predicts around 1/2 of the gravitational wave frequency today. And you may notice this 1/2 is the target or near the target frequencies for the next generation gravitational wave detectors. KP is again the peak of the K mode in the curvature power spectrum. So I'm going to, so this is K mode. So this and x-axis is K, the whole wave number, and y-axis is the power spectrum of this curvature perturbation.
Which curvature corresponds to a given K?
Right?
What is the curvature that corresponds to a given K?
you mean temperature in the early universe?
Yes, when the mud enters.
I forget the exact number, but like this chemo is very early universe. It's much larger scale, much larger than electroweak scale.
Okay.
So it's like I forget the exact number, but like yeah, like it's somewhere between electroweak scale and the point.
I see.
So KP, like if we have some curvature perturbation peak, that's some KP. So that's a meaning of the KP. There was some peak of the curvature perturbation in this 2D plot. And here, of course, there's a lot of constraints and sensitivities. So here, there's a CMB and large scale structure constraint at very small k. And there's also sizable constraints up to k around like 10 to the 5 inverse megaparsec. But up here, we have very less constraint. And interestingly, this K mode is that produce the PBH mass around like 10 to the 14 gram to 10 to the 17 gram. And you can see for this K mode corresponds to around a few hertz is actually is within the sensitivities of next generation gravitational wave. So once we have kind of this small mass time of the black holes from the curvature perturbation, we can guarantee that we would see the gravitational wave from the same curvature perturbation in next generation gravitational wave. Okay, within this, like I can summarize the big picture of this work. So we think about the asteroid-mass prime of the black hole, and with the high rising of the Hawking temperature, it can give the gamma ray signals, and we can detect these signals in upcoming gamma ray observations. And if this asteroid-mass prime of the black hole is originated from small-scale curvature perturbation, then this also generates the gravitational wave signals. And we can have correlation between these two observables, and we can use them to measure the parameters for small curvature perturbation or the primordial black hole mass spectrum. One comment here is here I like assume the asteroid-mass primordial black hole is originated from these small-scale curvature perturbations, but it can be some other production mechanism. But a lot of production mechanisms also have the companion gravitation wave signal. So it doesn't need to be like small-scale curvature perturbations, but it can be any mechanisms that can give also gravitational wave signals. For example, there's a pulse of phase transition that also gives a similar feature. So we are just suggesting an idea that correlating these two, but we are not just fixing on this small-scale curvature perturbation. But we use this because this is an easy way to give lighter gravitational wave signals. And of course, each step here includes very interesting and complicated calculations, and I only have 20 minutes here, so I cannot describe all the details, but I give the main references we use here, so you may want to check this later. So, okay, with this big picture, let me talk about our analysis very briefly. So we consider two types of curvature perturbation. First is delta function curvature, delta function shape curvature perturbation, which is like this curvature perturbation has monochromatic K mode, like the co-moving wave number at Kp. Or we also think about the low normal scale, which has a peak at this Kp and some width. In the paper, we provide analysis for both curvature perturbations, but in this case, I'm going to consider only the log normal because it's more realistic. And in this case, we have three parameters: the amplitude A, and the width sigma, and the peak wave number Kp. Okay, then like for fixed curvature perturbation, we can calculate the gamma ray signals and the gravitational wave signals. For these two plots, we fix sigma equals to 4 and Kp equals to like around 10 to the 15 inverse megaparsec, and we vary the amplitude. For example, this orange band, the upper line is from the A equals to 10 to the minus 1.64. So we have exactly sigma equals 4 and K equals to 10 to the 14 inverse and A equals this number. We would see the gamma ray signal in this line. And this lower bound comes from this lower end, and we choose a band from the upper bound is that the largest yet still satisfying the current bound. For example, from the gamma ray signals from the Compel or Fermi, and the total PBH should be smaller than 1. That gives bound like here. This determines the upper bound, and lower bound comes from the this line is above the e-ASTROGAM sensitivity. So the primordial black holes from this band, from this band of the curvature perturbation, would be detected in future gamma ray signals in e-ASTROGAM. And in the gravitational wave signal is the corresponding gravitational wave signal from the same curvature perturbation. And you can see the whole band is actually lies inside the sensitivities of the next generation gravitational wave signal. So once we find the Asteroid-mass primordial black hole in the gamma ray signals, we also should be able to see the gravitational wave signals in DECIGO or video next generation. Okay, then with this, we can ask the question, how well can we measure the 3 curvature perturbation parameters using the gamma rays and the gravitational waves? To answer this question, well, we provide 3 examples of curvature perturbation. For each model, we pick sigma, AP, and the amplitude A. And other parameters are just derived from these 3 parameters. Here we can calculate of course, this is just log normal curvature perturbation from these 3 numbers. And we can calculate the mass density from this curvature perturbation, mass density of the primordial black hole, and pick around 10 to the 18 gramish, which is asteroid-mass. And from this, we can also calculate the gamma ray spectrum around NEB-ish. And from this, we can also calculate the gravitational wave signal. And here in this talk, I'm going to focus only on 2. And we can assume this curvature perturbation is true. Then we can calculate what's the signal in the gamma rays and what's the signal in the gravitational waves. And we can see what's the measurement from the each experiment. That's this plot. This is the 2D plot for 2 sigma control for each experiment for LISA, PBO, and e-ASTROGAM. In case of the model 2 is correct. So this black star is the model 2 point. And you can see LISA, PBO, and e-ASTROGAM, how much they can measure the parameter, how precisely they can measure. So from LISA, they can measure in terms of KP and A, there is not very good in this sense. It's 3 orders of magnitude in terms of KP and more than 1 order of magnitude in terms of A. But you can see here e-ASTROGAM and BBO can measure this parameter very precisely. And more important thing is e-ASTROGAM and BBO are anti-correlated, especially in terms of KP and A parameter. This is sigma and A parameter, but here they are anti-correlated, which means BBO has degeneracy for larger KP and larger A, but e-ASTROGAM has degeneracy for smaller KP and larger A. So once we see both signals, both gamma ray signals and gravitational wave signals, we can measure the curvature perturbation parameters very precisely. So this is another good thing of correlating the 2 observations. Okay, let me go to the conclusion. And so the conclusion is, if we get to see the Hawking radiation at e-ASTROGAM or any other gamma ray observations from primordial black hole produced by curvature perturbations, and we see also the companion gravitational wave signals in the future gravitational wave detectors. And this leads to a smoking gun signal for distinguishing the PBH from the other gamma rays. sources. So even if we see some signal in the gamma ray observations, you may say that that's from the other source. But if we also measure the gravitational wave signals, and we can make sure this is from the primordial black hole originates from the curvature perturbations, or if it's different correlation, then we can tell what's the origin of the primordial black hole. And addition to this, correlating gamma ray and gravitational signals allow the very precise measurement of the primordial curvature power spectrum. And as a future work, this is not directly related to the talk I just gave, but we still think about the asteroid-mass primordial black holes, because this is very interesting. It's produce very large temperature Hawking radiation. So if we observe such gamma ray from the asteroid-mass primordial black holes, then by looking at the photon spectrum, we can have the existence of dark sector particle that decays or annihilates to photons. So of course, primordial black hole doesn't care about the coupling between like standard model and then dark sector particles. As long as they have mass, then they can be just produced from the primordial black hole as long as their mass is smaller than the Hawking temperature. And if they decay to photons, and there's another signal that goes to photons, then we can tell from the photon spectrum that if there's such particle. So actually, asteroid-mass primordial black hole is a good source for look for dark matter as well. Thank you so much. So there was discussion earlier, but so I cannot tell that I don't have like on top of my head, but that's well above the electroweak scale and like below the Planck scale. But it's very high temperature for it's much larger than electroweak scale.
Oh, right. I think we remember that the 30 solar mass number.
Yeah, so it's much smaller, so it's like much larger temperature.
Isn't 1 megaparsec when about 100 electronvolts?
Yeah.
So I just 10 to the 9, that's 10 to the 11 to the 20.
Yeah, it is.
And you have 10 to the 14, something like that.
Yeah, 15.
So 3 to the 9. No, the only point source at that measure.
You mean point source for the yeah, you can think of the point source, but we of course we can think about the full range of the KP in terms of log normal curvature perturbations. Like of course it's peaked at certain wave numbers, but you have this broad band, so it's like integration of like different temperatures as well. But like yeah, of course, like due to the width, then it can be
in terms of the spatial resolution.
Oh, you mean from the primordial black hole?
Yeah.
You mean the gamma ray from the primordial black hole? So in this analysis, we assume the mass density of the primordial black hole is just proportional to the dark matter mass density. So it's not like there, like from for example, from the Milky Way, we would see a lot of like this mass of the primordial black hole proportional to the distribution of this primordial black hole is same as the dark matter distribution. So it's like of course like one black hole is point source, but what we will see is the collection of like from the bunch of like primordial black holes, if it's true.
At that time, structural formation is still okay. So you already have.
Yeah, it's the primordial black hole, so it is like produced a very early universe, and yeah, they are just there.
Does the gravitational wave signal drop off too quickly for from lower frequency gravitational experiments?
Like yeah, so of course that depends on the width of the curvature perturbation. Like the width we chosen here, like reasonable width is like should be less than 4, and the band is around this. So it, like yeah, of course like percent timing array is like way up here, and so yeah, you wouldn't see any gravitational wave from the pulsar yeah in our model.
So sorry, it can be, is that the top right plot? Is that the spectrum? The
Yeah,
spectrum of
yeah,
black
this
hole?
is e-ASTROGAM. Yeah, sorry for this. This is
Right, so that's, okay,
yeah,
so
so
you just,
this is mass spectrum.
so in the top left, then you get the mass
Right.
spectrum.
Right. Yeah.
Okay, that was question. Question two, I might have missed this, but how do you get the gravitational waves? I mean, these are not produced by the black hole, they're produced by the blip in the.
Yeah, so-
spectrum, so what's that?
Yeah, once you have this curvature coefficient, it directly copies the metric. So you can
Uh-huh.
just simply calculate the gravitational wave signal, but this is second order. So if gravitational wave signal is proportional to the power spectrum. So normally it's suppressed, but like we assume power spectrum has like large enough amplitude, so we can still have the gravitational wave signal.
Yeah, I don't relate to that, but how well can we know this spectrum on the solar definition?
Oh, yeah, there's a good question, but so gravitational wave is just like analytical calculation from the PBH. But like the tricky thing is from the curvature perturbation to the black hole mass. From the black hole mass to the Hawking temperature is also like well studied. Like from the there's a package called black hole, and you can also calculate analytically. Of course, there's some gray body factors that is a little like hard to get from the analytically, but from the black hole mass to the Hawking radiation and from the curvature perturbation to the gravitational wave is well studied. But the tricky thing is the curvature perturbation to the black hole mass distribution, because this is exponentially suppressed. So these black holes are produced from the density contrast larger than some critical density, and that's exponentially proportional to the power spectrum. So depending on the window function and like what format, like depending on the formalism, this black hole function, this black hole distribution can be very different, even for the same curvature perturbations. So here we choose the press checker formalism, and we just follow that. But potentially there can be a lot of uncertainties from here to here.
Yeah, so first of one question, you're saying that you're using second order perturbation theory for the gravitational waves, but also you're saying that you have like really big constant densities. So like, how you want to apply perturbation theory to something that have like a contrast density of bigger than one?
Oh.
So those are the two things. And okay, one, and the other one is that in principle, you can also have a third handle of the signal. But I guess, I don't know, like, my question is, it's useful or not? Because also you could have the gravitational wave coming from possible binaries of primordial black holes. That will be like a third, but I guess they're gonna be emitting like gamma, right? So you first you see the gamma rays and the inspire of the binaries of the primordial black holes.
Okay, so so first question for the K mode we are interested in is very less constraint, so we can have like order one each amplitude. Of course, it's very constrained for like in the region for very small K or very largest larger scale. We have very tight constraint. This small band is only allowed region measured from the CMB and larger scale structure. But for larger K, we have very less constraint, like only from the BBN here and like pulsar timing arrays. And for this K mode scale, we don't have very large constraint here.
It's not about constraint, it's about theory. You are using linear theory, second order induced gravitational wave. But then you use like your density constraint is huge.
Yeah,
So
yeah,
it's
yeah.
kind of like you're describing black holes using perturbation theory. That doesn't add up into my mind, but yeah, I mean, what is the thing that I'm thinking of?
Okay. So first of all, it's not exceeding one. Still, of course, there can be like larger errors, but yeah, still we can use the perturbation theory because it's like the higher order is still suppressed. Well, because the suppression is not like as large as like for very smaller scale, but still we can use the perturbation theory to estimate the gravitational wave signal. And sorry, what was the second question?
I'm going to take it. Also, you have a third signal that could be possible, but it's the merge of possible binaries of primordial black holes that will be in the really high frequency.
Yes. First of all, that's just one time, and this is gravitational wave is stochastic. So like yeah, you see like it depends independent of time and the position. This is like a stochastic wave signal. while from the merger is just like one time. So
Yeah.
there's a time dependence.
But it's there, it's possible to be there, that's my.
Yeah, it's possible to be there, but like, yeah, of course, you measure like normal time. So of course, there's some overlap and you can just like, yeah, remove that part from the analysis for the stochastic gravitational wave signals. So I think it's different to look for stochastic gravitational wave signals and gravitational wave signal from the merger.
But what we learned from Nancy is that it's better to have like one event than the stochastic gravitational wave, because it's something that is more big, right?
For these ones, I calculated for the asteroid mass
Yeah.
black holes, I'm looking to like using LIGO data to put constraints on primordial black holes and merger of one asteroid mass primordial black hole with a 2.5 solar mass. If we have merge that you can start constraining the LIGO. So you can do it constraints, but
Okay.
it's gonna be hard to go much below and
Okay. Okay. Thanks.
Any questions?
Yes, two questions. Do a small scale perturbation lead to astromass black holes? And could there be other mechanisms responsible that we know of? And follow up on that, are there constraints in the existence of the asteroid-mass black holes?
Oh, so you're asking, so like for here, we can calculate the how much we can have the primary black hole, and there can be the constraint from that.
I guess the first part is just asking if those small scale perturbation lead to the asteroid-mass black holes.
Yeah. So the mass of the primary black hole only depends on this K mode. So if we have like this band of this K mode, like if we have like larger curvature perturbation between this K mode, then we can have this mass primordial black holes.
And then the second part, I guess, is asking, could there be other mechanisms for making asteroid mass black holes?
Yeah, so like I think I mentioned during the talk, and like there's can be like first order fluctuation that can also produce asteroid mass primordial black holes, and that also gives gravitational wave signals and gamma ray signals, and we can also see the correlation between them. And there's another mechanisms that can produce such as primordial black holes, but yeah, this one is the simplest and powerful. Yeah, you can just solve larger curvature perturbation, then yeah, you can have this.
Now let's thank Jae for